Hello everybody and welcome to today's presentation about airborne infrared observatories. There was a series of 3 of these observatories and each based on the experience of the one before. For today's presentation I have 2 small improvements. One is I have a new microphone. I hope it's better than the old one. And the other one is I will put all the web addresses I used in the description. Here again, as in this series of presentations, the outline is first history and motivation of the observatory, then the equipment, no geography as in the ground-based telescopes because these ones can fly, then a couple of results, and I think I omitted the outlook because it's clear more or less. First, about some specifics of airborne observatories. As I told you, there is no geography, so what you observe has to be checked with the pilot, because the pilot will determine where you can point your telescope on the airplane. And this results in these funny flight trajectories that these observations have. You have one straight line more or less per observation, and then the airplane turns around, and then you have another straight line, and then it turns around. You have another straight line and it turns around. So you more or less you can tell that the observatory observed 4 objects during this trajectory, and it started and landing in California. And a classical application for airborne observatories have been solar eclipses, and one very notable special case was made in 1973 when the then still new Concorde observed a solar eclipse for 74 minutes. That's a record, I think. And the maximum speed of this airplane is 2,179 kilometers per hour, and the speed of the shadow on the Earth is a bit faster than that. They say 2,400 kilometers an hour, which is close to the equator. If the solar eclipse is high latitude, the speed is even faster, and then it's impossible especially with today's airplanes, to keep up with a solar eclipse. Then here we can see the 3 steps: Learjet, and then the Kuiper Airborne Observatory, and in the end the Sofia, which already stopped working now, so the series broke. The funny thing is that the Kuiper himself, the astronomer, used to travel with this Learjet, but not with the Kuiper Airborne Observatory, at least as my sources said. The Learjet observatory was called Galileo, and there were 2 different jets that have been used, Galileo 1 and 2, but most observations have been done by Galileo 1. And they were called Galileo because one of the observers was able to observe the Galilean moons from up there. There you can see them by eye because they're actually bright enough to be seen by eye. But in the Earth's atmosphere, if the atmosphere is normal thick as we are on the ground, then you can't see the Galilean moons because Jupiter overpowers the light of the Galilean moons, but from the height of an airplane you can actually see them. And here are also the dates given, but I will report them more accurately later. And just to say that very shortly, observations in mid and far infrared are much easier to do on an airplane. I mean, we discussed ground observatories that go up to 5,600 meters, and with these jets you can fly at 12,000 meters, so that's a lot better when it comes to leaving the CO2 and the water below you. And here the size of the telescopes are given in comparison to the size of a person. Then for the equipment I will just refer to Kuiper and Sofia. The Galileo had a relatively modest telescope, a 40 centimeters infrared telescope. The Kuiper observatory had a 91.5 centimeter Cassegrain telescope and could observe in a wavelength range between 1 and 500 microns. And here is an image of the telescope. So the hole in the side wall of the airplane was relatively small. There, just enough for the telescope to look out. And you can imagine what wind drafts you have if you open up a jet in normal flight. For the Sofia telescope, it flew on a Boeing 747, and it was a 2.5 meters telescope. Some sources say 2.7 meters, but only 2.5 meters could be used from its mirror. And this one worked between 0.3 and 1,600 microns. So on a very, very broad range. And you can see here, as compared with Mauna Kea, Hawaii, of course, which is not the highest ground observatory for infrared, but the difference is huge in this part of the spectrum as to how much light you're getting. And there were 6 instruments for this telescope on Sofia. I can't tell you exactly which one was for what imaging and spectrographs. And the elevations possible were between 20 and 60 degrees altitude elevation from the airplane. And it used an inertial stabilization. So probably the telescope was hung up in the airplane, and then because it has some weight, not all the movements from the airplane go on the telescope, which is a very, very difficult thing to do, technically speaking. And the pointing accuracy was 0.5 arc seconds. Then first some results from the Galileo observatory. I'm almost tempted to say Galileo airplane. It looked at eclipses too, and observed the planets, and also made observations of the Jacobinid meteors. Because I'm also working with meteors a little bit, I want to give you a short summary of these meteors. Normally meteor streams are named after the constellation where they come from, but the Jacobinid meteors are an exception from that rule. They come from Draco, but they're named after the comet that made these little bodies. And they are very slow meteors and come from behind the Earth, so they're one of the few streams that can be observed in the evening. And this is an example shot of a Jacobinid meteors, and this stream sometimes can make huge displays with even meteor storms. People talk about a storm when you have more than 1,000 meteors per hour, corrected for limiting magnitude and assumed they are coming from the zenith. And also the Galileo observed comet Ikea-Secchi, which was a very, very large comet back in 1965. It's a very old picture before the time of electronic cameras. For the Kuiper Airborne Observatory, KAO, it had a similar profile. It looked at planets, it took spectra from Mercury, it definitely confirmed the rings of Uranus. These pictures I'm showing here, of course, is not made from KAO, but from the JWST. One of the best pictures of Uranus taken from close to the Earth. And it also measured Pluto's atmosphere. It looked at protoplanetary disks, which is a classical application of infrared telescopes, and also at supernova 1987A. But here the picture I'm showing you of this splendid, lovely supernova also is not from KAO, but from Hubble Space Telescope. Actually looks a bit like a planetary nebula, but of course a supernova has a completely different form of remnant, much more various forms also than planetary nebula. Then for Sofia, with the even larger telescope, the yield is even more impressive. One thing is that it found water on the moon in the Clavius crater shown here. And it also looked at Pluto's atmosphere and measured nitrogen, methane and carbon monoxide up there. This has been done during a stellar occultation observed over New Zealand, and this shows the advantage of airborne astronomy, because you couldn't have done this otherwise. If there's no observatory in the small stripe that the occultation makes on Earth, you have no chance. But if you're on an airplane, you can of course start there. And this also is an image of the atmosphere of Pluto, not taken by Sofia, but by the New Horizons probe that looked back. So Pluto has the sun in the back, and that's the easiest way to take a picture of the atmosphere. Then this one is an image I like a lot, which is the center of the Milky Way, but it's an overlay from 3 different observatories. Everything you see in blue and green is from the Sofia telescope, and the red is from the Herschel Space Observatory, which made a survey of the whole center of the Milky Way. I reported on Herschel in an earlier presentation on space infrared telescopes, and also data from the Spitzer Space Telescope is shown in white here. And as we know with the infrared, you can see deeper into clouds. That's why it's important for the center of the Milky Way that is very dense. With normal visible light astronomy, you couldn't do that. Another nice example is that the Sofia telescope took pictures of the Horsehead Nebula and centered on carbon monoxide and carbon itself, and therefore it could measure the split up of the molecule by the light, probably, or ultraviolet light. So the different colors show different molecules, molecular states of the CO or C. And here is a visible image for comparison, which actually has been done by an amateur astronomer and well-known YouTuber, Dylan O'Donnell, in case you want to visit his channel. So these were the results of the Sofia telescope. Of course, these were just some I found in the internet, but it has certainly done a lot more work over the years. So thanks a lot for the attention.